The process begins when the action potential travels down a motor neuron towards a muscle. When the action potential arrives at the synaptic knob at the motor neuron, it causes voltage-gated calcium channels to open.
Calcium ions flood in and attach to synaptic vesicles containing acetylcholine. The attachment of the calcium ions causes those vesicles to go under exocytosis and leave the synaptic knob or action terminal. When the acetylcholine enters into the synaptic cleft, it drifts across and attaches to receptor proteins on the sarcolemma. After the acetylcholine attaches to the receptor proteins, it causes them to open up and become more permeable to sodium ions. The sodium ions will then rush in by diffusion, causing the inside of the muscle to become depolarized or positively charged. At that point, that depolarization travels across the sarcolemma and even down the T-tubule. When sodium ions are present down the T-tubule, it forces calcium ions out of the sarcoplasmic reticulum.
When sodium ions are present down the T-tubule, it forces calcium ions out of the sarcoplasmic reticulum. When calcium ions leave the sarcoplasmic reticulum, they go in and diffuse into the myofibril itself and surround the actin in the myosin. But in specific, they attach to the troponin portion of the tropomyosin complex, causing the troponin-tropomyosin complex to change shape, exposing the binding sites on the actin protein. The myosin heads can then form a cross bridge with the actin, and then using ATP, pull the actin towards the center of the sarcomere.
If you want to relax, you have to ship the calcium ions back out into the sarcoplasmic reticulum using active transport. We do this because taking them from a low concentration to a high concentration in the sarcoplasmic reticulum, when a person dies, rigor mortis will set in 3 to 4 hours after death. Why? Because you don't have any ATP to remove the calcium. And it peaks at about 12 hours, and then it will dissipate 24 to 48 hours once your body starts to decay.